we're working on the production of 2D nanoplatelets in the liquid phase by the process we term liquid phase exfoliation. I would like to introduce you to the process in general, but then also focus on recent work where we try to apply this to organic sheet stacks. So most of you are familiar with all the inorganic materials, transition metal dichalcogonides, for example, but there's many more. And I would like to show you that this process can actually be very versatile and applied to materials that are otherwise not investigated so far. Okay, so with this in mind, here is an overview in general what we do in my group. We work on this liquid phase exfoliation. We produce these nanoplatelets in the liquid phase. So here, for example, in each vial, you have a dispersion, we call it, where you have these nanoplatelets suspended in the liquid, and the different colors come from the different materials. The process works in a simple way. So the idea is you impart high energy, and this will lead to mechanical exfoliation. For example, also involving shear forces that are randomly occurring in the liquid. However, as we will see, the exfoliation, so the peeling of the sheets, is not the only process that happens. We will see that we also chop down the material in other dimensions. Nonetheless, we get these platelets, and when we know how to stabilize them in the liquid phase to prevent their reaggregation, we get these stable dispersions. And the way we do that is we use certain solvents, or we use soaps, aqueous surfactant solutions. These will then cover the sheets and prevent the restacking in the liquid. As you will see, this material that we produce is extremely polydispersed, so we have different lateral sizes and thicknesses. So what we do a lot in my group is we try and develop size selection techniques. We have standard techniques, but we're also trying to push this forward to have a size selection, for example, isolate small or large nanosheets, depending on what we want. And from there on, we take the dispersions and investigate, for example, simple size dependent properties. I will show you a couple of examples there. We work on the controlled deposition. I will also show you an example there. And since we are working a lot with materials that are little explored, we also investigate the degradation of these sheets. So with this, I mean whether they react with oxygen and water. This I will not cover in my talk today. This is a quite long and interesting story, but not for today, maybe for some other time. And we're also working on the surface modification, especially for transition metal dichalcogonides. But also here, I will not cover it in my talk today. So let's begin. So this is an overview of the materials that have been investigated with liquid phase exfoliation in my group, or together with Jonathan Coleman, where I did my postdoc. We started, of course, with simple ones like graphite or group 6 transition metal dichalcogonides, but then also moved to other materials. So you can see boron nitride on the slide. This also works just fine. The layered pnictogens, such as black phosphorus, also work fine. Also, all other sorts of transition metal dichalcogonides, 3,6 semiconductors, etc. So I will just say etc. here, because indeed there is no material we found where you cannot produce a stable dispersion. They will not have the same quality, as I will show you, but you will get a stable dispersion using a very similar process in all cases. The advantage here is also we don't need high quality crystals, big, beautiful single crystals. We chop them down anyway. So we can live with powders, and therefore it's easy for us to investigate materials that are not commercially available and provided by collaboration partners. Here you see some examples, and often these collaboration partners cannot make large single crystals, but more powdered materials with powdered texture. So here the liquid exfoliation process is an advantage over beautiful sheet isolation by micromechanical exfoliation, for example. So I will begin with talking about these materials because this was our starting point. And I already said we always get stable dispersions, but how well do we exfoliate and what does this depend on? So what did we learn about exfoliability by using these standard inorganic materials? Now to do that, we first need to take a look how a sample, a typical sample, looks like in terms of sheet morphology. Now this is tungsten disulfide produced by tip sonication aqueous surfactant solution without any size selection and just deposited for atomic force microscopy. And you immediately see the beauty of the polydispersity. It's a very nice image. The sheets are isolated from each other, but some of them are so small you can hardly see them on this 10 by 10 micron image. And others are so thick that they're almost bulk-like. So clearly we need to do something before we even try to analyze this image, because when a sample is so polydispersed, you will have problems accurately determine the size and thickness distribution. So we said, okay, no matter what we do, we always need to do a size selection, and we want to do a size selection that we can use for different materials and different liquid environments. So it has to be something simple and general enough. And we found this liquid cascade centrifugation that we introduced 5 years ago actually does the job. So what do we do? How does that work? So we take our dispersion, we centrifuge at low centrifugal accelerations, and we obtain a supernatant, that's the top part, and some really heavy and thick stuff will sediment. So in the first step, we discard this because this is unexfoliated. We take the supernatant, go to the next step at higher centrifugal accelerations, and again, we will find some material in the sediment and some will stay in the supernatant. We separate the two and collect the sediment. And this will be large sheets, heavy mass material, but already nanosheets. Now then we take again the supernatant, go to higher speeds, and so on and so forth. We repeat this for as many steps as we like. So usually 5 to 6 size selected dispersions are produced from a single sample. After each step, we collect the sediments, and the advantage here is you can exchange the liquid. So for example, if you used a surfactant before, you can redisperse without surfactant. Or you can exchange the solvent, for example, if you had a high boiling point solvent such as N-methylpyrrolidone, which is popular, you can replace it with another one that is less toxic, less high boiling or whatever. So this is why this actually is quite nice, and we can do it for the different materials. Now let's take a look on the morphology side, what the centrifugation actually does. So let me show you an example of graphite in this case. So this is an image of the graphite stock dispersion, just as polydispersed as the WS2. Image might not be as nice, but still. So what we do now is, or what we do in general, is we measure the sizes of the sheets. So we measure the longest dimension, that's length. The dimension perpendicular, we term width. The two of this will be, so to say, a measure for the area, and then we measure the thickness, which we convert to layer number. And when we do that, for a graphite stock dispersion, we can see that the lateral size ranges from 10 nanometer to about a micron, and the layer number from 1 to 30 layers. Here, each data point is a single sheet that was produced and measured with AFM. Now, after the size selection, you can immediately see from the images that they're much better, that they're much nicer looking. The sample is less polydispersed. It's still polydispersed, but not as bad as before. When we look at the population, what the size selection did, it sliced the population of the nanosheets in an angle. And when we plot the length as function of layer number, this is very clear how we can understand the size selection. Now, this green boundary that I sketched here, we can move this depending on the centrifugation conditions and then isolate our size selected fractions this way. Now, there's something I would like to point out, and that is there are no large and thin sheets, and there are no small and thick sheets. The absence of large and thin sheets we initially thought could have something to do with the size selection by mass in the centrifugation. But actually, when we look at the stock, we also see that there are no large and thin sheets. So the question was, why is this so, and what is the mechanism behind it? So to look at this, it's not so convenient to always look at these data clouds. It's sometimes better to look at the averages of the fractions. So what we will do in the following, we will take the arithmetic mean of length and thickness, and all red data points will collapse into one data point, which is the mean. So when we do that for the very same data, area plotted as function of layer number, we can see that there is clearly a power law relationship between lateral size and layer number. Each data point, as I said, is the average that we take from AFM statistics of one size selected fraction. So here we made 5 fractions, 5 data points. So this is for graphite again, or still, and yeah, we see this power law. Now, how does it look like when we use different materials? Do we see the same thing or something differently? And this is shown in this plot. So here I added in other materials. So the reddish ones, for example, are transition metal dichalcogenides, and green here is gallium sulfide. These guys here are hydroxides. What you can see is in all cases, you have this power law relating the area to the layer number, but there's a difference between them. They're offset from each other. So for example, when we look at a certain thickness, say 3 layers, then we see that the transition metal dichalcogenides will be much smaller than graphite. And gallium sulfide would be smaller. Still, there we can even hardly make something that is 3 layers or enrich a sample with 3-layer sheets. So this really shows that we can get a figure of merit for the exfoliability. And the way we approached this was that we said, okay, we fit this empirical power law and extract the prefactor, which is the length, or the characteristic length of the monolayer. So if we had a sample just with monolayers, this would be the lateral size of it. So this we termed characteristic monolayer length. And we can extract it for all the different materials. And this means we can test what it scales with. So for example, does it scale with the binding strength between the sheets? So we tested this and we found that this was not the case. I will keep this very short. It's a 6-year project that finally came to an end a couple of years ago and involved many different groups also from physics. And what my colleagues from physics did was to develop a simple model, which in the end predicted this scaling law that we observed. And the idea, the answer for the model was that we do not only achieve exfoliation, but that we also have scission. So we break bonds in the plane as well. And therefore, so when we imagine this, we have these 2 processes occurring when the energy input, or when it's with an equipartition of energy, when the energy that goes in goes equally into both processes, you can understand why you don't have large and thin sheets, because large sheets would have overall a larger interaction between the sheets. But at the same, so you need more energy to exfoliate them, but this energy also goes into breaking the sheets. So this is the idea behind the model. We tested whether this, and the model, the end of the day, told us that the characteristic monolayer length divided by the crystallographic thickness of one layer should scale with the ratio of in-plane, out-of-plane binding strength, and it should scale in a linear way. And for equipartition of energy, the slope should be 2. And here we plot our experimental data from these fits versus computed in-plane, out-of-plane modulus ratio as a proxy for the binding strength. And you can see that we indeed observe such a linear scaling with a slope of 2. So this really means that how well we exfoliate, how large our sheets are for a given thickness, this is determined by the crystallographic structure of the material. It's a material property. It's not governed by the exfoliation process. We've done a lot of work trying to confirm this, and we believe that so far that's really the main part of the exfoliability in the liquid phase. Okay, so this is what we've learned from all these materials that are reasonably well known. What happens when we move to other materials? So to these organic sheet stacks that I promised you. And I will show you some examples. So organic sheet stacks, I call them organic because they mostly contain carbon. They do contain some other atoms as well, nitrogen, oxygen, or even metal centers. But still, I call them organic sheet stacks. I hope chemists can forgive me for that. So here are 2 examples. These are so-called 2D polymers made from Dieter Schlüter's group in Zurich. And these are actually very interesting structures. They're porous, and they actually come, as van der Waals crystals, so to say. There's other examples. For example, from Dresden, we received this guy here from Xinjiang Feng's group. In the SEM image, you can also see that it's actually a layered structure. But this is now a so-called metal-organic framework, so it's a coordination compound. So here you would have copper centers attached to these ligands, and these ligands are organic moieties, and the way this is built up again is a sheet stack. There's more of these metal-organic frameworks. These guys here, I don't want to go into detail with the structure, just bear in mind there's a lot of layered materials in metal-organic frameworks or 2D polymers. They can come in very different exotic structures with different metal centers, different packing motifs, etc. So these ones we received from Norbert Stock-Kiel. We started our work with the polymers from the Schlüter group, and the reason is the way they're made ensures that they're single crystalline. Whereas for the way the coordination compounds, metal organic frameworks, or also covalent organic frameworks are made, they are not intrinsically not single crystalline. They will have some polycrystallinity crystal domains that are attached to each other, but some grain boundaries or so. And sometimes there might even be some cross-linking. So this is not the case for the 2D polymers from Dieter. This is why we started with them. So let's take a look what happens when we take this guy here. When we look with the AFM, we clearly see that there's quite nice nanosheets produced. They're often folded. And when we determined the yield of the exfoliation process, it's typical for liquid phase exfoliation. I put it here to also give you this sort of idea on the numbers. So here it's plotted as function of a centrifugal force. And depending on the size selected fractions, it ranges from like 1% to 10%. So the yield is quite low, and this is the yield of monolayers, which is even lower. But importantly, there are monolayers inside. And when we look at our graph where we plot the area, the average area as function of layer number, we see that this material is as exfoliable as graphite. So it has a similar characteristic monolayer length. And graphite so far was the record because it has such strong bonds, and we can understand this in the structure because we have sp3, mostly sp3 carbon network. So the bonds are quite strong, not as strong as in graphite in the plane, but there's also groups sticking out here, reducing the interaction between the sheets, and that's why it works so well. So this means that in principle, it should be possible that chemists can design materials that are particularly suitable for exfoliation when considering how they need to adjust the in-plane, out-of-plane binding strength. We also, for this material, we went into more detail. This was work done in Ute Kaiser's group in Ulm with Hao-Wan. And he looked at TM and actually saw that the structures are crystalline. Sometimes when they're folded, you get these diffraction rings. But in some cases, you actually see that you have the individual diffraction spots. We also checked with vibrational spectroscopy and could confirm that, well, we don't do damage to the sheets, at least not to the extent that we can see it. Now let's look at another one. Let's look at this one. This is also 2D polymer from the Schlüter group. You see beautiful single crystals, almost even the same dimensions in the starting material, nice hexagons. And when we do our exfoliation and size selection, yeah, we destroy this beauty and produce a big mess. So we can see also that we do not keep this hexagonal shape of the platelets that we have initially. And this is really a manifestation of breaking also the bonds in the plane and not just peeling the layers apart. Again, we can do our AFM analysis and count a lot of nanosheets. So here is area again plotted as function of layer number. Each data point is a single sheet. The different colors are different size from different size selected fractions. And again, when we draw a comparison, we see that this material is even better exfoliable. So it's now here the black trace, and red is the graphene and green is the polymer we saw before. And here the monolayers are even larger. Okay, now what about our metal organic framework? You can see already from the images, from the AFM images, it might not look as nice. It has a beautiful color though. And when we do our analysis here, again, just the one parameter plotted versus the other, we can actually see, if we compare it directly, the data clouds, we see that these sheets are laterally much smaller for the same thickness. You can also already see it because we don't even produce monolayers. And this is really a problem for our analysis for the metal organic frameworks. What we therefore do is we use the real aspect ratio of length and thickness to describe the exfoliability, because when we're so far away from a monolayer and cannot produce monolayers, then it's not so nice to speak about characteristic monolayer length. So here we use the length thickness aspect ratio, and this is plotted here as function of centrifugal force, and you see it's between 4 and 6 in the best case. So something with an aspect ratio length to thickness of 4 is not a 2D material for sure. It's some sort of nanoplatelet. So we believe that this is the case for these MOFs, not just because the bonds in the plane might be weaker, but also that there might be issues with the polycrystallinity. This is yet to be confirmed. Now, just for completeness, this is the result from the metal organic frameworks from the group in Kiel, from Norbert Stock's group. Let's focus on this graph here, which shows the aspect ratio. And here also the colored ones are these MOFs. The black is graphite, and this is MOS2. Note that this is on a log scale. So you see here also the MOFs are not very well exfoliable. There's one guy here, that's this red one, ODB2, which reaches almost the same aspect ratios as MOS2, but this has an intercalation layer already in the crystal structure. So probably this is why it's likely better to exfoliate. Nonetheless, the end of the day, what we can do for sure is we make liquids that have different lateral sizes and thickness distributions, and we know them. So the question is, can we learn then something about size-dependent properties for these novel organic sheet stacks that are not investigated? And here, I actually just want to refer you to Alexei and remind you very, very, very briefly in a very crude way that a combination of dielectric screening and confinement effect changes the excitonic response in the transition metal dichalcogonides, for example. So in the bulk material, the excitons will be delocalized over the entire crystal, and we will have a relatively low binding energy. And when we actually go to the monolayer, we know that on the one hand, the gap widens, on the other hand, the excitons are localized in these two dimensions. This is where all the fancy physics comes from. And this results also in a larger binding energy. What we measure in an experiment, when we just measure an absorbance, extinction, or reflectivity spectrum, is this difference here. So we measure the exciton energy, which will always be the combination of gap and binding energy. But empirically we found for all inorganic materials that have excitons, so really all semiconductors we've looked at, the exciton energy scales with the layer number in an exponential way. This is what we know from the inorganic materials. So we can say that this is clearly a characteristic of 2D materials, of dielectric screening and confinement. Now, how about the organic sheet stays? Do we see this? Well, let's begin with our 2D polymer 1 from the Schlüter group. Here again, you see the structure. When we take extinction spectra, so we measure the intensity of transmitted light as function of wavelength, we see there are changes. I don't want to go too much into detail. Some of these changes across the size selected fractions are due to contributions from scattering. I don't want to bog you down with that. I just want to focus on the peak positions, assuming that these are from excitons. Now, we don't see much, therefore, what we always do, we take the second derivative. And when we do that in this spectral region where we have a peak, it's quite beautiful that you start to see that it's not just a single peak, but a series of peaks with a vibronic fine structure of the molecule. And we do see that there are some shifts occurring. Now, when we extract the peak positions from the second derivative and plot it as function of layer number, we do observe this characteristic exponential shift that we observed. So we could say that, yeah, clearly in these materials, there are characteristics of 2D materials. What about the other one? Is it always like that, or was it just a lucky guess? So let's take this one. Again, I don't want to go into too much detail with the spectrum. Here you can clearly again see that there is a background signal, and this background is quite strong, and from scattering we wanted to get rid of it, so we measured in integrating sphere. And here you see the result from the size selected fractions. We see a funny signal here in the smallest, thinnest material isolated at high G. And this is this red stuff and the gray stuff in the pores. It is a template that was used for the synthesis. And when we exfoliate it, it's released. So that's this. But when we look at the other transitions, here we see beautiful vibronic fine structure. Even when the second derivative, even when we zoom in, we can try as much as we want. There is no shift. So how do we understand this? Well, these peaks come from the aromatic units in the structure, and in this material, they are actually perpendicular to the plane. So they stand upright to the plane. So this means they don't care whether there is another plane on top or not. So whether or not you have, whether you observe such effects, of course, will depend on whether the aromatic units or the units where the excitons are localized, whether they actually feel the other layer or not. Okay, now the last few minutes, I actually want to take you even further away. And the idea is, well, the idea is that the liquid phase exfoliation breaks any bonds that we have. And when they don't have the same strength, we become some funny morphology. So for 2D materials, we get 2D structures. The idea is that it doesn't need to be a layered crystal that we subject to this process. And actually, some other groups have been working on non-layered materials, such as pyrite, iron disulfide, or even germanium or whatever. And they could observe that because there is some anisotropy in the crystal structure, that you actually get something like platelets out. Now we wanted to do it differently. So the problem is when you take a non-layered crystal and you chop it down and break all bonds, then these bonds will have to saturate with oxygen or water, so it will actually react. So we said, why with the environment? And I said, well, why not go the other way? Why not take a material that is a purely van der Waals material? So also just composed of molecules all held together by van der Waals and pi-pi interactions. And pi-pi interactions are quite strong. And the question was, would they be strong enough to partially survive the exfoliation? This is a project that we did together with Jana Zaumseil in Heidelberg. The paper just got accepted yesterday, so if you can actually find it online soon. It's in ACS Nano. The idea is we took rubrene. This is a famous organic semiconductor. So you have these rubrene molecules, and they can pack in different crystal structures. But there is no covalent bond between these molecules. The blue ones and the blue units here are the pi-pi units. So this is the pi-pi stacking direction. So it can be orthorhombic or triclinic. You can make it yourself. And depending on which crystal packing you want, you have to do a different synthesis of the material. Then we subjected these crystals to liquid phase exfoliation by bath sonication in aqueous surfactant solution. And as you can see, we observed colloidal stable dispersions. So this is the UV light photos. There you see that in the case of triclinic rubrene, you even get quite strong photoluminescence from the rubrene molecules here. Here again, the different numbers stay for different size selected fractions here. We didn't want to focus on the size selection, rather use this as sort of purification. And the purification actually worked when we look at the AFM images. So this is the intermediate fraction, and this is the fraction at higher speeds. You can see that this is already quite nice looking. And the important thing is it's rods. So we thought that by looking at the crystal structure this way, that we would cleave here between these gray moieties, and the blue ones would be our pi stacking direction. But you have to turn around the crystal, of course. And when you do that, you see that you will actually end up with one-dimensional structures. So here is a little statistics of the rod sizes. For the other rubrene polytype, polymorph, the triclinic rubrene, we actually observed these nano belts, or rather nano belch bundles. When I first saw it, I thought it was copper nanotubes, but it's actually not. It's really the rubrene. And these can be very thin, down to like 1 to 2 nanometers. So there can be even individual rubrene nanobelts that can be produced. This is the Raman. I don't want to go into too much detail. The rubrene has a very characteristic Raman spectrum. Depending on the polytype, you have a slightly different spectrum. This is all understood. The gray one are the crystals in these figures, and the red and blue ones are the size selected fractions. And we see the same peaks in the exfoliated material. The triclinic one is exactly the same. For the orthorhombic one, we see additional peaks. And this additional peak is known to be a surface disorder at the surface. Well, clearly when we do exfoliation, we expect that. And this here should also be active in the crystal, and this depends on the crystal orientation. And in our rods, this is random, and in a single crystal, it's fixed. So that's why we only see it in the exfoliated material. Again, we teamed up with the people in Ulm. Again, Hawan took a look with the TM, and this is absolutely challenging because these structures are very sensitive under the electron beam. So he really did a great job here. This is an example of a nano rod, and there you can clearly see in the diffraction image that you have relatively sharp diffractions. By essentially modeling this diffraction pattern, how one could suggest the main cleavage planes, or the main cleavage plane, the main cleavage planes, both of them. So one, so it's held together by these stronger pi-pi interactions. So one is in the AC plane, so going like this, but there is another one then going like this, where there's also no pi-pi interaction between the sheets. Looking at the nano belt, this is really objects that are easily missed when you look with the TM, and here it's not as nice. We actually only saw a diffraction ring and no sharp reflections. But this is probably a belt bundle, as we know from the AFM analysis. Most of them are bundles, and they will not have the same orientation. They are crystalline, this is why they give a diffraction ring. But yeah, so to say, in this way, they're polycrystalline. So here it was a bit harder, but we just followed the same arguments regarding the cleavage plane. So here we suggest that the cleavage plane is parallel to the a-axis. So the a-axis is the pi stacking direction, and all the planes parallel to this, we have the cleavage, and therefore we get the 1D objects. So with this, I would actually like to come to an end. I took my time. Usually this talk can be given in much shorter time, but I actually enjoyed explaining things in more detail. As a take-home message, I wanted to show you that liquid phase exfoliation is a versatile production technique for nanomaterials. And really the versatility is what counts. The sheets will not be perfect, they will be small, not only monolayers, but you will be able to apply it to a whole host of structures. The morphology that you obtain, the end of the day, is a result of the in-plane to out-of-plane binding strength. So it can, to some extent, already be predicted. So we can, for example, at least to some extent, predict for a new material, can we make monolayers or not? For the part on the organic crystals, we believe there are issues when we have samples that are polycrystalline, such as these metal-organic frameworks. But given the progress of the organic chemists and inorganic chemists working on the synthesis, we believe that this will improve significantly over the next years. And finally, I showed you that the concept of liquid phase exfoliation can be applied to purely organic crystals where molecules are only held together by pi-pi stacking and van der Waals interactions, or any sort of, let's say, non-covalent binding. So in this case, we looked at rubrene, and we found that we can produce one-dimensional structures that are in dispersion. So with this, I'd like to thank my team. Currently, the team is very small because we're building up the new group, but also the former team members, of course, here, especially Kevin and Guillermo, and Angelina, who did an internship with us, and of course, the collaboration partners. The material producers are always the most important ones, because without them, we would not be able to do our research, or at least not this sort of research that I showed. And for the project with the rubrene, also Jana, and of course, Hawan in Ute Kaiser's group in Ulm for the TM. So with this, I would like to have a quick announcement at the end. If you're working on material production on a large scale, then I would like to tell you there is a special issue in Baustein Journal of Nanotechnology. This is all open access for free. And Gustavo Canfado and I are the guest editor. So if this is something you could contribute, we're happy to receive a message from you. And with this, I'd like to thank you for your kind attention, and I will move to my summary slide. Thank you.